Okay, we're getting into week 10, and we have a quiz Wednesday. I'm going to hand out and a test on next week. I guess we'll have to hand out a practice test. I'll get that out to you on Wednesday. We can look at that on Monday. I think homework, was homework 3 due this weekend? Yeah, cool. So experience was okay with that, pretty straightforward. Making your own stacks and queues. Assignment what? Really? Okay, yeah, that's what I like. It really said to upload a jar file. Yeah, I like to see the code just because it's easier for me to grade that way. You mean on the assignment it says to upload a jar file? I think that's because my old uploader was automatically going to extract those. I don't have that anymore. So where does it say that? I just yeah, just ignore that. This thing has gone through so many incarnations. I'll have to delete that. Thanks for the heads up. So we're doing a lab on recursion today. Oops, we're doing lab 8, not lab 10. Hello? And the recursion. And the reason we're doing recursion today is because the advanced sorting, so we learned a little bit about sorting last week, and you got to make your own sorting method. And those are basic sorting operations. We're going to take a little closer look at the advanced sorting operations, sorting methods, specifically merge sort and quick sort on Wednesday. And those methods are recursive. So we're going to have some kind of preliminary exposure to recursion again, although you should have had this already from 10a. And I'm sort of wondering what I actually have in here. So let's download the lab here. Go to the downloads folder. Try that again. No. This guy. And there we go. Yeah, so we do have some lecture demos we'll be doing, and gosh, now I'm trying to think how I did this. Rather than listening to a boring lecture, although this can be helpful too, so we'll kind of do both. I know I do something with a ray. I think I might have to cover that array thing today. So anyway, let's get started a little bit, and we'll kind of noodle through here and just make it. So recursion isn't terribly hard. You've seen recursion before, right? You've all seen recursion before. This is a cartoon involving some people playing a role-playing game, and in that role-playing game, somebody wants to create a role-playing game, which would be, I guess, illegal. Plus, it'd be kind of a headache to keep track of all that. Yeah, so recursion is a pretty it's easy to fall into recursive type situations. There's also a lot of recursion in films sometimes. Has anyone seen the movie? Well, Primer. Primer is a film about time travel. Has anyone seen that? Has anyone seen Primer? It was kind of a sleeper hit. It came out in, like, I don't know, when did it come out? 2007 or something? 2004. And it involves a lot of people doing, I mean, a few people doing a lot of different small time travel jumps. And it becomes recursive in the sense that they jump and then they jump again. Anyway, it's yeah. This is the people actually have. It's such a confusing film because there's like two characters and they're jumping. They can go back in time, but they can only go back. The interesting thing about their time travel is they can only go backwards at the same rate of speed at which you go forward. So if they want to go back 8 hours in time, they have to sit in a box for 8 hours. And if they're going to go longer, they have to bring food and stuff so that they can stay in the box long enough to go farther back. So they initially make a lot of money by going back like 8 hours and day trading. Because if they, at 4 o'clock, you know what the stocks are going to be. You go back 8 hours, you can make a fortune that way. But then they start playing around with some other things. They start doing some experiments and they screw some stuff up, and then they have to fix it. Anyway, and then they end up putting, I think they end up having a double jump. They put it, one of them, they start to fight each other. And anyway, it's a fascinating story, and nobody can really understand. It's all very impressionistic. It's hard to really follow what the sequence is, but they are recursing in the sense that they're, and recursion is pretty confusing, right? It's a great film if you want to just sort of get the feel of it. And they're actually like these two inventors working in a garage that kind of stumble on time travel. It's a really fun movie. It's kind of a thriller too. Yeah, you should see it if you get a chance. Does anyone else? Any other films involve recursion? Anybody know? A film that's kind of like that is Existenz, another kind of movie from the 2099 era. It was kind of a fun film. And that's where they in some future world, there's a video game that you plug into your nervous system, and it takes you into an alternate reality. And it's sort of an organic thing. That's the video game controller, this thing right here. It looks like some weird mutant thing from a lab, a bio type lab. And you have to plug it into your spine. It's really kind of gross. There's like a lot of gross biological, like nasty kind of stuff in it. But then when they're in that virtual world, they find another game to play that takes them down another level, and then it kind of gets confusing about what level they're in. And then when they come back up, it's, not clear that they're in the same reality in which they started. I don't think they are. So you kind of get lost in the recursion, the repeated jumps into other levels. And so computer science people would, these are things that you would sort of, you would kind of relate to, because when you're coding, these things kind of happen a lot. So two good examples of recursion. And, in real life, just like say recursion, some of the best sorting methods are recursive. Some things that that are hard to do with iteration can be really easy to do if you have a recursive feature in your language. And not all languages have recursion. Some languages don't allow it. Some languages only use recursion when you want to do repetition. They don't have loops. They just have recursion. So yeah, it's a very useful thing, and just something we're going to kind of master. So, so we are going to process an array using recursion. So we're going to see how that works. And we'll spend a little time talking about the efficiency of recursive methods in terms of data, how you can use recursion helpfully, and also stupidly you can use recursion poorly to make a bad solution, and a couple other specific details about recursion. So we could start with an example in the lab. This lecture demo file kind of shows you a main method, and one of the things we could do in the main method is call a countdown of, say, 5. And when we call, countdown, not count me, countdown of 5, we jump into countdown with the number 5. And in this method, we print the number n, and then if n is bigger than 1, we call a countdown of 4. And you keep repeating that over and over again, and you can trace that. This actually would be probably a good one to trace with the debugger. So let's try clicking here. Wait. I guess I have to compile first. Compiles. So I can put a breakpoint in there at countdown of 5, and it's kind of cool to see that in operation. If you run the main method, you're going to stop at that line. And you can click on step into to see what happens. And in step into, we have a local variable n, which is 5. And you would step over the print statement to print the number 5. 5 comes up. And then you step again, and n is greater than 1. So we're going to call a countdown now of n minus 1, which is 4. So we step into that again, and now we are another layer down. Notice this is a stack that's building up here. We started in main, and we called countdown, and now we're in countdown another level down. We called countdown a second time, right? And we're still back in countdown, but we're in a different version of countdown, right? And we can click step and print out the number 4 showing up here on the lower left. And we click step again, n is greater than 1. So we go, now we're going to call countdown of 3. So we step into that, and we get another version of countdown on our stack. And in this version, n is 3. Now I imagine if you click on these other versions, you can see what these other versions had, right? See the first, see here's main, and doesn't really have anything interesting going on, but countdown, the first countdown in the stack has n equals 5 on it. The second countdown is a version where n is 4. There's another version of countdown where n is 3. And all these methods are building up on the runtime stack, waiting for one of them to start returning. If we continue to step, we can step into another countdown where n is 2. We can do another step and step into a countdown where n equals 1. And another step. And oh, I stepped over. Should have stepped. Well, actually, no, n was no longer greater than 1, so that was it. So this method, when n equals 1, is going to finish. And when we do another step, we are back. I guess they all cleared out. That's funny. It all just cleared them all out real fast because they all returned at that point. There's nothing really to do when we come back from those. Once we come back from those methods, they all finished. So the whole stack kind of got cleared out right away, and we're back in main. And when we're finished, it will just say, that's it. So that is sort of how recursion works. You can see those method calls building up on the stack over and over again until you're all finished. Another example would be a method that returns a value. So this is first recursive method is a void method, so it's just printing stuff out. But you can also have a method that returns something. So we could make a statement to print out sum from 1 to 5 equals, and then we'll just say sum of 5. And again, we can compile this and put a breakpoint in there, and it's kind of cool to see this going. So we're going to terminate this previous execution, and let me take out the breakpoint on the other place. I think that one's still there. So go back here. No, I guess it's gone. So so we will. And you will see that we should be stopped right here, doing the sum from 1 to 5. And at this one, I think we should be able to step into, hopefully I did that right. Let's do a step into. Yeah, and now we're in the call to sum. And we're in the call to sum where, again, the local variable n is 5, which is what we passed to it. And we're not at this base case, so we're going to say else sum equals sum of 4 plus 5. So we're going to step into, and now we're in sum of where n equals 4, right? And we're going to step and step into sum of n equals 3, step into, step into, and so we've built up again all these things. And what's happening here is the computation can't really finish. We can't really tell what the sum of the numbers from 1 to 0 are until we start coming back from a base case. And so these, where the else is, this is the general case where we're actually calling ourselves, again, the method that we're in is calling itself with a smaller value of n. That's the general case. And we're waiting, and eventually by doing that, you're supposed to eventually run into the base case. And the base case is when n equals 1. That's when there are no further recursive calls. You can see that here. We just assign the value of 1 to some, and then we return. And as we return, then the previous iterations of that method call can be resolved as well. And so here we are right now. We're about to step into when n equals 1, and so n equals 1 now. So sum equals 1, and if we do a step, we're going to return a 1 to the previous caller, which was sum of when n equals 2, right? So here we are doing a step. Does this make any sense? Are you guys following this? We do a step, and we're going to return. So one of these gets popped off the stack, and now we're in the version where n equals 2. And sum of has returned the value of 1. And when n equals 2, we're going to basically just add 1 plus 2 together. And it should be nice if it told us what the return value was, but it's not. We could have assigned it to a variable and then seen it, but it's returning, oh yeah, there's the sum of 3 because it's 2 plus 1. And it's going to return this value to the next caller, which was when n equals 3. So we step again. Now we're on n equals 3, and we do a step, and now sum is going to equal 6 because we added the 3 to the previous result. And each time we're popping off another frame from the stack and getting closer and closer to the bottom. And then we return, and then we can print out the final result, which shows up on our console as 15. If you have 5 plus 4 plus 3 plus 2 plus 1, you get 15. And the cool thing about recursion is you can do that without any for loops, no while loops. There's just if statements and method calls, right? So you got an if statement and an invoking of oneself, invoking the method calls itself again repetitively until it actually develops the answer. So that's recursion in a nutshell. Any questions on recursion? Or anything we just went over? There's a certain conceptual kind of framework you have to do when you're working with recursion. When you're writing a recursive method, you have to realize that method's going to be called a lot of different times. And you have to sort of think about all those calls leading up to the final base case where the final answer comes in, and then working the answer back to the previous calls until you get the final result. That is recursion. So the idea about recursion, and this is the beautiful thing about it, it's a way of solving a problem by breaking it into smaller problems that are actually fairly similar. And when the smaller problem is identical except for size, then that's called recursion. And you keep doing that until you break it into smaller and smaller pieces until the known solution is reached. Just like what we showed you in BlueJ, you can sort of play with friends. You can sort of go down the line here. If I want you to, if I want to count down from 10, I could just say 10 and have someone next to me, like Vincent, start counting down from 9. Vincent would say 9 and have Hector count down from 8, and so on. And eventually, someone's going to get down to 1, and then they pass the word back that I'm done, and that word keeps passing back to all the other people in line until the whole process has finished, right? So that's recursion. There's the countdown method again, and very straightforward, just calling itself. So passing a value, printing out the value, and then calling itself on a smaller value. This is the same technique that people use to create these powerful sorting methods that we talked about last, quick sort, merge sort. Other sorting methods, heap sorting. you're going to be asked to design some recursive methods. And it's really a chance to kind of think through that process of, how do you actually frame it right. So when you're designing a recursive solution, you want to think about what part of the solution can you actually, when in the general case, what part can you sort of solve along the way, and what smaller problem that has a solution that, when taken with the original contribution, it provides a solution to the original problem. So actually, no, the first part here is asking you, what part of the solution can you contribute to directly? In other words, what part of the solution has an obvious answer? And that part of the solution is, this is what we call the base case. And then the general case is when you can sort of break the problem down into smaller pieces, and when you combine everything together, you get the total solution. And then figuring out when the process ends. What smaller but identical problem has a known solution? Have you reached this problem, or the base case? And there could be multiple base cases in the more general problem. There's actually a kind of a fun, if you're looking for motivation, some of this stuff is kind of basic, but there's actually a pretty cool application in the lab, what we're going to do. At the very end, there is a problem of a checkerboard that you can imagine, an 8x8 checkerboard, which has a dollar value printed on each of the squares. And if you can place a checker on the board anywhere you want, and then move it across the board with standard diagonal moves, everyone knows how to play checkers, right? You can, well, it's actually just moving one move diagonally in either direction, right? But the point is, every time at every point, you have a choice of moving in one or two different directions. And you can solve this using recursion by at every point you would sort of invoke the sum method twice, and it would explore all the different ways of navigating your checker piece through the board until you get to the far end. And it would actually compare the results that it's getting, so that when it comes back, it has the maximum value that you could get from moving your checker a certain way through that checkerboard. So that's a really powerful technique. This is sort of the last problem you get to solve and tackle. And it's a really fun one to sort of think about, all the parts of that. But to get there, we have to first work with some basic recursive problems and get the confidence to be able to extend this to more challenging applications of recursion. So the method has to receive the input value. That's the argument. The method contains logic, and that's basically if statements. No loops in most recursive methods. Most recursive methods don't need loops. And so if you're writing a method that has a loop in it, you're making a mistake, because if you put a loop in a recursive method, you tend to end up getting like an infinite loop or infinite recursion. One or more cases should provide a solution that does not require recursion. That would be the base case or the stopping case. And one or more cases must include recursive invocation of the method. There is a problem that happens if you don't design your method right. Like, for instance, what if in the sum method, and let me just kill the debugger, and if I go here and get rid of the breakpoint I had, what if I said I want to compute sum of -5? I want to calculate the sum of the values from 1 to -5. What do you think is going to happen? Passing a sum of -5 is going to do what? Mark? It's going to try to go on forever, because it's going to keep subtracting 1 from -5, and you keep subtracting 1 from -5, you're going to go farther and farther away from your base case. So this method is vulnerable to crashing. But in reality, you can't go on forever because of what? What do you think is going to be keeping it from going on forever? Memory, the memory needed for what? The stack that has all those calls stored on it, right? That thing runs out of memory, you can't go any further. So you can try this if you just pass a -5 to that. Let's go ahead and compile and run this. You can see what happens when you don't have your method designed properly. It says something here. Oh, come on. Go there and show me. Oh, that's weird. It's actually, I guess it's telling me some information, but it's not allowing me to click on there. I want to see these messages. And it's in an infinite recursion. And I guess if we scroll up, we can see what the problem was originally. And the first problem was Stack Overflow error. Where have you seen Stack Overflow before? Yeah, it's the forum for programming kind of questions, right? Stack Overflow, a very common situation when you're working with recursion. It also implies that you're kind of overloaded with information, which is kind of typical for computer science students, right? Stack Overflow error. And it's telling you, and the question is, how many times did it invoke itself before we overflowed? Well, if you counted all these lines, that's how many. It's tracing your call all the way back to main. But I don't know how many there are. There's quite a few pages here, and each one has about 20 calls on it, right? So it's probably in the 1,000 or so range of calls before we ran out of memory for our stack, our runtime stack. So how could we rewrite the code so it doesn't do that? Yeah, you could check if it's a negative number and then count upwards, I guess. You could do that. Or you could just say, you know what, if it's negative, just forget it, right? So you could just say if n is less than or equal to 1, just say it's 1. At least you won't get that Stack Overflow anymore, right? So that will make your base case capture those problem situations where you have a negative number throwing in there, right? So it's not going to give you an accurate result. If you want to get an accurate result, you might have to redefine more than that. But you could at least stop the Stack Overflow from happening. A recursive method that skips n lines of output where n is a positive integer. That will be pretty easy. A recursive algorithm that draws a given number of concentric circles. Here's some examples of that. Skip lines, taking a given number, would, if it's greater than 1, it would print a line and then call itself again with a smaller value, right? That'll skip so many lines. No loops, just using recursion. Drawing a concentric circle is a little more like a graphics problem, but you draw a circle and then you change the circle so it's like 4/3 bigger, and then you call it again. And this tells you how many times you're going to do it, and you keep doing that as long as you have a value that's bigger than 1. So tracing a recursive method is kind of challenging, and why don't we, yeah, there's a couple different ways of tracing a recursive method. you're going to be asked to trace recursive methods on the next test and in the drill exercises. So looking at a recursive method, you're going to be asked to kind of read it and try to figure out what it's going to actually print or compute. And we can show you how to trace a method like the countdown method so that you can apply it to other methods. And this is kind of showing you the sequence of calls. You know, countdown of 3 is going to display 3, call countdown of 2, et cetera, et cetera. You can do it that way. You can also trace the recursive calls using a stack that kind of grows downward. Here's the main method, okay, calling countdown of 3 and printing that 3. And you notice everywhere there was a parameter, you're just putting in the value of the parameter. So that 3 is over here, it's over here, and that becomes 2, and so on. You're kind of working your way down there. And then when this method returns, you return to the bottom of this method, and you return to the bottom of that call, and then you return over there, and you're done, right? So we start in main, and we go down through several layers of calls, and then when those finish, we come back up to the top. And you can also imagine the activation records of all those method calls kind of stacking up in front of you, or just kind of going off in the distance as they're growing and shrinking. So let's do the lab activity, which is on tracing. Let me download this thing so we can do it together. And I guess I need to save this. Oh, it is there. All right. There it is. Another way to trace a method like sum of is to lay it all out in a sort of an indented form. So I kind of like this approach. It's pretty convenient, right? When you say sum of 4, you're going to have to jump into sum of, you know, every time you jump another level down, you indent further. So this is calling sum of 4, and in sum of 4, you're going to calculate sum as the sum of 3 plus the sum of 4. Well, that sum of 3 has to be done with another recursive call, so we indent even further, right? And then in this level, we got to calculate sum of 2. Well, that's another recursive call. And every time we call that method again, we jump in further indentation. And then when this method is finished, it returns, say, a 1, which then allows this one to return a 3, which comes back to fill in that, so that we can then return a 6, which comes back into this, so that we can return a 10 for the whole thing. So there's just a bunch of different techniques you can use to trace a method. And this is a stack diagram where we start at the bottom if you want to grow upwards, although as you saw in the lecture, you could also grow downwards if you want. But here we are, you know, the stack is growing, and sum of 4 is asking us to compute sum of 3. So sum of 3 is going to return sum of 2, and then sum of 2 is going to calculate that. Sum of 1 is going to calculate that, and then the values are passed down This way, this one goes there, this guy goes there, until we get the final answer of 10. Okay, well, here's a recursive method called f, and it's calculating a result. And if n is less than 1, it's going to make the result equal to 1. Otherwise, it's going to compute f of n over 2 plus 1. And this is done using integer division, right? So you all know what integer division is. You know how that works. So you can sort of figure out, as you keep dividing a number by 2, eventually it gets to 0, because 1 divided by 2 in Java is 0. It's not 0.5. So you can try a couple tries here. I'm doing it this way using the stack that grows up from the bottom. So f of 16 is going to return f of 8 plus 1. Recursion doesn't always count down. What you do is you start with the argument that was given, and then you follow the instructions in the method. And when there's a recursive call, you've used the value that it's passed to the recursive call. Yeah. When would you want to use recursion? When most of the time loops are just fine. But as I mentioned, some of the best sorting methods are recursive. And those are really complicated methods. We're doing really basic stuff right now that you could do much easier in general with a loop. But we're learning the mechanics of recursion. So you might think this is sort of silly, but it's actually kind of practice for the really more challenging stuff we're going to take on bigger and bigger problems. Yeah, it's really powerful technique. And we're going to look at a few different ways of dealing with recursion for arrays and stuff too. So yeah, a lot of times we're looking for the application, and we're going to see that on Wednesday more. But today it's kind of just practicing the mechanics. So as you see, and if you have this thing handy here, right, f of 16 is going to set result equal to 0. And then n is not less than 1. So the result is going to equal f of 8 plus 1, right? And so there we go. F16 is going to return f of 8 plus 1. Well, that means we have to now write f of 8 above it. And f of 8 is going to return f of 4 plus 1. Well, that means you're going to have to write f of 4 above it and continue. And when those finish, you're going to eventually get to the base case, which will then start to have values that pass back down the stack, so you get the final answer. So try that and figure out what the answer is, and we'll see if you got it right, and then we'll come back and offer any corrections if you have any questions. Oh, this is when it's 0, returns 1. Yeah. Questions? So F8. Now I got to come to F4. F4. What's F4? Well, you see that when that is 4, and you do F4. Is that true? No. So you have to make result equal F of F of 2. Yeah. So that's F4 is going to say return. F of 1 is going to return. Trouble understanding. I know process, but I'm not sure how to get it. What is that? F of 2 is called F of 2. Because you kind of calculate that in the next frame of it. And when you do F of 2, you're going to have to calculate F of 1. Right? And you got to calculate F of 1 first. You can't know the answer until you come all the way to basic. F of 1 is going to return F of, what does that say? Whoa, what does that say? 0.5. Because you have integer division, what does that say? 0. So return F of 0 plus 1. Right? So F of 0 is going to give you what? Code. When n is 0, what does it return? Okay, so it returns 1. So it's going to say return 1. So scratch out the 0.5. F of 0 is going to be 1. 1 and 2. Yep. Well, I would do this. We're really going to. These are all steps. At the 4, I can actually and you could, if you want, but you would start with them. Yeah, that's it. That is correct. It's what's the answer? 6, right? Yeah. Because F of 4 is going to have to calculate and return F of 2 plus 1. And so that means we have to calculate F of 2, which is going to return F of 1 plus 1. So that means we got to calculate F of 1. Well, that's going to have to return F of 0 plus 1. And F of 0 is just going to return 1. That's the base case. So that 1 plugs into F of 0 in the previous call, right? So that this guy is going to return 2, right? Because 1 plus 1 is 2. So that's going to plug into there. So that this guy, for F of 2, is going to return 3 into this place right here. So that F of 4 is going to return 4 into this place right here. So that F of 8 can return 5 into this place right here. So that F of 16 can return 6. So the answer is 6. Now, if you don't like that stack frame diagram, you could also do the indentation approach. I kind of like the indentation approach maybe a little better, but it's just another shorthand way of doing it, right? So in other words, if you want to do f of 16, you could do it like this, and f of 16 is going to calculate, what do you want there? Yeah, it's going to say, you know, result equals f of 8 plus 1. Well, that's going to make you say result equals, you know, because this is the indentation here, result equals f of 4 plus 1. This is going to set result equal to f of 2 plus 1. This is going to say result equals f of 1 plus 1. And this is going to say result equals f of 0 plus 1. And this is going to say result equals 1. And you're indenting, and you know, if you're just doing it on scratch paper, I think it's a little bit, maybe a little bit easier to do it this way. What do you think? I don't know. What do you guys like? Do you like it this way? And then you're building downwards, which maybe is a little more intuitive, plus kind of matches the way you write on a piece of paper. And you plug in, this value comes in here, replaces that with a 1, so that this guy gets replaced with a 2. You know, or as I was doing it here, I think I just said it returns, so you can write out the word returns. Maybe that's even a little bit better. So this is going to return a 1. This is going to return a 2. This is going to be a returning a 3. This is going to be returning a 4, returning a 5, and this is going to return a 6. This is return, which is, you can't read my writing. That's short for return. Okay, so another way to do it. Anyway, if I give you a recursive method like that, you should be able to trace it and noodle your way through it. That's a really good technique to have. You have to be able to read these things before you can write them. Okay, questions so far? Okay, so to continue, what about a method count up that counts from 1 to n, where n is a positive integer? A recursive call will occur before you display anything. This is kind of an interesting situation. Suppose you want to count up. Let's do this right now here in the lecture demo. Suppose we want to do a count up. So let's make a public static void count up of int n. And the hint was that the first call has to be the recursive call. What would that look like? How are we going to count up when we have n here? We want to start at 1, but we don't really, you know, we don't really have a 1. And we have n, right? We don't have 1. So how do we count up from 1 when we have n? Create a new variable and set it equal to 1? No. That's sort of going, we tend to go back into loop thinking real easily. Think about it recursively, right? If we could solve a simpler problem and then just add a value to the end of it, what would that simpler problem be for counting up? Always start at 0 or 1? No, that's not quite the simpler problem. A slightly simpler problem, if you're trying to count up from like 1 to 10, what would be the slightly simpler problem? Sorry? Instead of -1 plus 1, no. That's kind of like what you would do for a loop. You're not thinking recursively. What would be okay, I want to count from 1 to 10. What's the slightly smaller problem from counting from 1 to 10? Count from 1 to 2, but that's too much smaller. What's a slightly smaller problem from counting from 1 to 10? 9 to 10, nope. 1 to 9. If I could only count from 1 to 9, that's the recursive. You got it, right? Ding, right, that's it. And the bell goes off when you get it, right? If I could just count from 1 to 9, then all I have to do is print out the number 10. And now I've counted from 1 to 10. Okay, that's the kind of thinking that it takes to write a recursive method. You have to sort of think about the slightly smaller problem. So the idea is that, well, let's just do count up. It's the same thing. It's the same problem to count up from 9 as it is to count up from 10. But I'm just going to say, well, let's just assume we could count up from 1 to 9, right? And then at the end, I'm just going to print my n, which is 10, right? The only thing is I need if statements here, because if I don't, what's going to happen? Sorry? It might go past 0. And in fact, it will go past 0. You'll have a stack overflow. So what kind of if statement do I need? What is the base case here? What's the base case to count up to? It's so simple that I don't need to do any further recursive calls. If I was going to count up to what would be the simplest possible value I could count up to? N, no. That's general. Huh? 10 minus 1? No. What's the simplest thing? If I asked you to count up to something and you didn't need any further recursive calls, what value would you count up to? 1. Who said 1? Alicia, right. Yeah, you'd count up to 1. That's trivial. So when you do a count up where n is 1, you just print out the number 1. And you're done, right? That's the trivial case. That's the base case. So we like to kind of usually start the methods with the definition of the base case. You don't have to, but the base case would be something like if n equals 1. And if you want to protect, oops, I'm doing the wrong method. So let me scoop over into count up. Not return though, this is a void method. So if n, you could say less than or equal to 1. Yeah, if n is less than or equal to 1, you're just going to print out the number 1. Otherwise, now you know that n is bigger than 1, so you're going to call count up on n minus 1 and then print out the value of n when you're finished. Recursion involves a certain amount of faith or wishful thinking. If only I could solve this slightly smaller problem, then it's real easy to add on my new version, my new variation to get the total solution, right? For when n is whatever it is. Okay, well, we're gonna have to call this to make it work. Let's just change our call to countdown to call it count up. Or leave countdown if you want and make another call to count up. And maybe after some, I don't know, just so you have a record of all these things. Might be nice to keep them in play here. So we're gonna call count up of, let's try something different like 7. And let's make sum of go up to, say, 3. So we're going to call count up of 7, and we should see the numbers 1, 2, 3, 4, 5, 6, 7 if we did it right. And there we have our numbers that counted up from 1 to 7. Right? It's a little weird to think recursively, but it's really powerful if you can think about it that way. It allows you to do a lot of interesting things. Okay, questions? Now, there's a few different ways of doing this. Let's see what the solutions have for this one. This one just has a simple, if n is greater than or equal to 1, count up of n minus 1, and then print line of n. So this doesn't even have an explicit base case. It sort of does, right? The base case here is what? The value that makes this condition false. Because this is selecting the general case. If n is bigger than or equal to 1, call count up of n minus 1, and then print n, right? So if n is 0, what's going to happen? Nothing, right? But if n is 1, it's going to call count up of 0, which is going to print nothing, and then it's going to print the number 1. So that would actually work as well. It's a little simpler, right? It's a little simpler. You don't need to explicitly identify the base case, but it kind of helps initially when you're getting started to kind of write that out, I think. Recursive methods that return a value. This is the sum of method that we looked at already, and those values, you know, are building up a result that then gets passed down to successive versions. Write a recursive value method that computes the product of the integers from 1 to n. That would be pretty similar, but instead of adding, you would be multiplying. But you would initialize your result to 1, and the base case would be, you know, if n is 0, the result is just going to be 1. Otherwise, you do n times the product of n minus 1. So that's fairly straightforward. Okay, questions so far? What about arrays? Well, it turns out you can work with arrays recursively as well. So you can make recursive methods that actually process arrays. And this is kind of a preview for the advanced recursion methods for sorting on Wednesday. But suppose you want to make a method to display all or part of an array. Here is a method called displayArray that takes an array and the first and last index of the values that you want to look at. And you could make an iterative version and recursive. What does iterative mean, by the way? Iterative, yeah, it means using a loop. While loops, for loops, whatever. Versus recursive. Well, here is a method that displays the array recursively by printing the item at first in the array. And then if first is smaller than last, it's calling displayArray on first plus 1, because you've already printed out first, right? If you just print out the first item, you can then recursively call yourself starting at the next one over to the last. And as long as first is less than last, it will keep doing that recursively and printing the next item out in the array, right? But you could also start with the last item and change the way you organize your recursion, right? So you could actually say, all right, well, what if I checked first to see if first was less than or equal to last? And if that's true, I'll just invoke the call again on if only I could print out the items from first to last minus 1, that's sort of the wishful thinking step, then I could just print out the last item in the array as well, right? So that would also print out the array recursively, right? Now, I think both of these are defined in here. Let me see, in my lecture demo. I think we have some of these in here. Down here, there is a displayArray and displayArray2 and displayArray3, which will actually solve all these things together. These are actually kind of fun. So we're going to make an array to display first. So let's make an array. We'll say int square brackets data equals, open curly braces, and then a bunch of values like 3, 8, 4, 5, 1, 9, 2, and 0. And we would invoke our method by saying display array of data. And the first index that we want to display is going to be 0. What's the last index we want to display? Well, I think I have 8 items in here. 1, 2, 3, 4, 5, 6, 7, 8. So the last index would be 7, right? Yeah, if you had a really large array, you could say, yeah, you could say data.size. You could say, or. You could use data. Actually, with arrays, there's no parentheses. Is it length or size? I forget. I think it's length. Yeah, data.length minus 1. No, length holds the number of items. So the length variable holds the number of items in the array. So right now, length would be 8. No, you don't have to make the length variable. It is already defined for every array that you create. Yeah, there's an internal variable called length. Because arrays are actually sort of represented by classes, by objects, and there's a length variable that keeps track of the length of the array. So you can say data.length. Nope. Yep, this is an array. Yep. And yeah, so you would say data.length minus 1. Mm-hmm. So we go here, and here's the instructions. Print the first item in the array. If we haven't finished printing, do the recursive call on the rest. So we print the first item. How do we know if we haven't finished printing? How do we know we haven't finished printing yet? Marco? Well, if the first equals last, that's probably about the time to finish. So if first is less than last, or equal to, I think if first is less than or equal to last, right, then we haven't finished yet, right? So there's still more work to be done. So then we would just call display array of array, and we would go from first plus 1 to last, right? So last stays same, but the first item is increasing 1 because we already printed 1 out, right? And it's kind of convenient with arrays to just print them all on one line. I think that's what I was getting at. Instead of doing a print line, why don't we just do a print? And that's where that space comes in. So the items will be kind of spaced after each other. And if first is less than or equal to last, we'll call display array of first plus 1 and last. And then we want to get a new line at the end of all this. So what do we do to get a new line at the end of all this? What could we do? I think we would say else. And we could just, this would sort of be our base case. Okay, let's see if that actually works. Is there what's going on here? Uh-oh. Looks like I have a Stack Overflow. No, array index out of bounds exception. So it looks like I might have gone too far, right? Let's see. Oh yeah, because I'm printing first. So I think I need to say is if first is less than last, right? Then, okay. Well, it's using an index to refer to different, it's not really counting per se, but it's using an index to go to a different point in the array. And first is sort of accumulating one, yeah, closer to last. It's getting closer and closer to last, right? And there's our array all on one line. Okay, so that is one way of printing out the array. Another way is to invoke the recursive call first, and then do the last item in the array. So the idea is we're going to print array last. And that's not going to happen until we printed everything else first. So we invoke the recursive call first. So we could say something like, display array 2 of array. And in this case, we want to go from first to last minus 1. And if we haven't finished printing all the items, we'll print all the items up to, but not including the last one. So, oh wait, that's the thing. So, sorry, let's do this down here. If we haven't finished printing all the items, print all the items up to, but not including the last one. That's this guy here. So if we haven't finished printing all the items, then we're going to do this. But how do we know we haven't finished printing all of the items? I think it's sort of the same idea, but we have to sort of think it out though. Let's see if if you think about it, all right, so if first is 0 and last is 7, we're going to call display array of 0 and 6, right? And then we're going to print everything out from 0 to 6 and then print out the last item. But inside there, we're going to have to call 0 to 5, 0 to 4, 0 to 3, 0 to 2, 0 to 1. I think it might have to equal the same. So let's just see if first equals, if first is less than or equal to last. And then we'll print the last one. And let's see. So if first equals last, gets a little perplexing, right? So we'll have to sort of figure this thing out. Let's see if that's going to work. I think we're going to be having an issue here. Maybe we're going to go too far down because Well, let's just try it and see what happens. And it looks like we are in a recursive loop here. What's happening? Did I call? Oh, maybe I didn't call it. Yeah, you're right. Let's go back here and call it. So we have to call display array 2. And I got another array out of bounds exception, -1. So I think we went too far. Again, let's just set if first is less than last. And there they are, one right after the other. The only problem with this version is it's hard to figure out where to do the print line, right? I don't think you can, I think someone figured this out last year. But recursively, and maybe the idea, well, let's see. You know, for this one, it's kind of nice because when you get to the base case, you can go to a new line, right? Because you're going to end up kind of reaching the end of the array. But since you're doing this backwards, you know, you can't really print out the new, you know, since all these guys are going to go, well, maybe you could. Maybe it's just an else statement. Let's see. Because each one of these is going to eventually print out something. So you can't print new lines after each one of those, can you? Because then, yeah, so you need some way to actually kick in a new line at the right time. And I know it can be done, but I'm not going to figure that out right now. So, and that's not terribly important. What we can do is, you kind of get the idea basically on how that works. You can basically start, you know, this is sort of a formatting thing with the spaces. And you can start, you know, with a print statement and then the recursive call. Or you can start with a recursive call and then the print statement. But there's one other option, which is a little confusing, but this is actually how the binary search algorithm. It's a way of breaking up the array in half. And you would compute the midpoint of the array. And what if you, you know, for a given first and last, you invoke the algorithm on the array to the left of the midpoint and on the array to the right of the midpoint, and then put that back together again. So let's see. It's a midpoint algorithm to divide up the array in half. It then invokes itself again on both the lower half and the upper half. This is somewhat similar to how binary search algorithm works and other recursive algorithms like quicksort and merge sort. So it's kind of helpful to kind of see this. It's just a simple application. If the first and last indices are the same, print that index. So we should have an if statement here. So if first equals last, we're going to print that index. Otherwise, we're going to find the midpoint. Let's use open curly braces find the midpoint between first and last. So we're going to say, you know, int mid equals, and the midpoint is like first plus last divided by 2. You're just going to average them, right? So if first is 0 and last is 4, the midpoint is 2. If first is 0 and last is 5, what's the midpoint? It's 2 again, right? 5 plus 0, 5 over 2, which is 2 in Java, right? First plus last over 2. So you could be a little bit off one way or the other, but it's close to the midpoint. Then we display the array recursively from first to mid, and we display the array recursively from mid plus 1 to last. So this is the recursive call. In this case, there's 2 recursive calls. And we're going to pass array, and we're going to say first to mid, and display array 3 of array mid plus 1 to last. This may seem kind of stupid to do it this way. It seems like a lot of extra work, but it is a helpful way of knowing that you can break an array into halves and sort of process the different halves separately, because that's the key to a lot of these powerful sorting algorithms we're going to look at later. And put a close curly here to close off the else block. Questions? And then let's call that, but we're going to have to put a print line, a new line in here, because this display array 2 doesn't really go to new lines very easily. So system out print line just by itself, and then call display array 3. And oh, we didn't say print line, so make it say print again. But you can see the items are coming out in order. So we'll just have to remove the ln from the print statement. Like so. And there comes out the third version, right? Okay, did you get all that to work? Any questions? What if I asked you to trace this? Could you trace it? That last one? Could you? But you could. It isn't that hard. It looks really confusing. And as long as it's confusing, you'll never really understand it. But if you can trace it mechanically, it just makes everything make so much more sense. You have so much more, you know, understanding of it, right? So let's see if we can trace it. I think we can trace it. Let's try it. So I don't know if you want to write somewhere. Is there some blank space on the handout? It looks like it fills it up pretty well, but I should probably leave more room for it. Actually, maybe under the coding bath thing there. Let's call it. So let's do a trace of a display array. And let's just do a, let's just do an array that has 4 items in it. So keeping it kind of small will kind of help us avoid getting too complicated. I think you'll get the same. You'll get basically the idea how it works if you can see it. Yeah. So this is the array, and this is the first, and that's last. Oh yeah, at the end, parentheses. Sorry. So what's the algorithm going to tell us to do? Well, does first equal last? No. So we're not going to print anything out yet. So the first thing we're going to do is we're going to calculate mid. So let's go in here. We're going to indent, right? And so what's mid going to equal the first time through? 0 plus 3 over 2 is going to be 1, right? And we're going to then invoke display array. And I'm going to sort of do this, we're probably not going to have enough room. Well, we might have enough room. No, we're probably not. But let's see what happens. So we're going to call display array. And what are the indices going to be? Who's tapping? Yeah, it looks like it's going to be, have to go from 0 to 1, right? 0 and 1. Because we found that mid is 1. So we're going to go from 0 to 1, right? So we might be all set to jump to now display array from 2 to 3, right? But we're not ready to do that yet, right? Because before we can go any further, what do we have to do? We've got to evaluate this, right? We've got to evaluate display array 3 of array from 0 to 1, right? So what do we have to do? We have to indent. So when first is 0 and last is 1, what's the midpoint? 0. 0 plus 1 over 2 is 0, right? So mid equals 0. And what do we have to do? Well, mid equals 0, so then we're going to have to say display array 3, right? Same array from 0 to 0, right? See that? Well, go do that. What is that going to do? Well, we're going to indent again. And what happens? At this point, whoops, got to go to here. At this point, first equals last. So we're going to display the first value in the array. That first value spits out. So it's going to, we can just say it's going to prints the 8, right? And then what happens? What happens after we print? After we print this 8, what happens? We're finished with that version of display array 3, right? So what do? We go back out to the level that we came from, right? We just did the case of this, so we're finished, right? So now we have to do the next in line for, after doing the mid of 0, we did this. Now we're going to do this call, right? And so what's that going to be in this version? It's going to say display array from mid, or from mid plus 1, which is 1, to last, which in this incarnation last is 1, right? So that's going to indent. That's another base case, right? That's going to print. They're both the same. So that's going to print the number 9, right? It's going to print the number 9. And then we've just finished, by doing that, we've wrapped up the call to display array 3 of 0, 1, right? This guy here is done. Right, so we would return to this level of indentation. I'm kind of running out of room here. And the next thing we would do is what? We'd be doing the second half of the array, the display array 3 of 2 to 3. See, so I'm going to do that in the text here, but if you have room, you can squeeze that in. We would be doing display array 3 of the array from mid plus 1 to last, right? And then that continues on and does the same type of thing and displays those other 2 items the same way. You can see the recursion is forcing you to go deep really quickly to get to that first item, and then you kind of come back out, and then you go deep, and then you come back out again. And that's sort of what's going to happen a lot with recursion when you're working with arrays. John? What's causing the number to change? You mean, how do we get to 2 and 3 here? Because the first time through, and this is the thing, this method is repeating a lot, right? The first time through, first was 0 and last was 3. And we calculated the mid was 1 in that case, right? And we then went and did display array 3 from 0 to mid, right? That was this line up here. And then we did all those, we went deep and did all those guys, and then we came back out, and we still have to do display array 3 of mid plus 1 to last. And when we first went in there, mid plus 1 was 2 and last was 3. So that's why we got the 2 and the 3 here. Isn't that cool? Yeah, it keeps track of everything, and that's the amazing thing about recursion. It's just, what does it look like in memory? You mean like the runtime stack? Well, the runtime stack is building up, right? And every time we do these calls, right? So we, we added, we called it first, then we added, the one for where mid is 1. And that was a stack frame for that version. And then we added another one for when mid equals 2. I mean, mid equals 0. And that was another stack frame. And then we had these temporary things added on for when first and last was 0. And then, but then that was, that was added, and then it was removed as soon as it finished the job. And then it added another one for when first and last was 1, and then it removed that. And then it was all finished with the mid equals 0, so then that's removed, right? And then it could add another one for like mid equals 2 or something, right? That's basically how that's, so the stack can be increasing and decreasing as it's processing this thing. Yes, it's automatically removing all these calls whenever they're finished. And the stack just kind of maintains the order of all that stuff. It's pretty cool when you see that working, right? It's and this gives you the power to trace anything, right? If you can just do this, it's just following these steps, and it's very mechanical, and just fearlessly, every time there's a call, you got to follow that call down wherever it's going, and you might have to go many layers down before you work your way back up again. Okay, questions? So that's a rather long lecture demo. There is another example of the towers of Hanoi, which I think, let's actually continue with the lecture slides a little bit. There's not too many left. This is the idea of dividing an array in half. You can kind of see again, a common way to process arrays recursively is to divide the array into 2 portions. And we do that with quicksort, we do that with merge sort. And that's showing you how to do that. We just did that. And here's how the binary search actually works. It's probably the most famous algorithm that splits the array in 2. It actually computes the midpoint value as first plus last divided by 2, just like we did. And then if first is greater than last, then we ran out of array to search. So we returned false, we couldn't find it. If the desired item equals the value at the midpoint of the array, we return true. If the desired item is less than the value at the midpoint of the array, then we do the binary search on the amount of the array that we haven't looked at yet from first to mid minus 1, just like we did with that display array method call, right? And otherwise, then the desired item must be greater than the midpoint value, so we call binary search on the value from mid plus 1 to last. In this case, because we're looking at the value at mid, we don't go mid to last, we go mid plus 1 to last. So this is how it unfolds when you're doing a binary search. You look at the middle entry. Well, again, you look at a search for 8. So we're looking, this is the target item. And the mid from 0 to 11, when 0 is first and 11 is last, is going to be 5, right? So we check the number 10 to see if that equals 8. Well, it doesn't. And in fact, 8 is smaller than 10, so we got to search the left half of the array. So we're going to search from 0 to 4. And the midpoint of that is going to be 2, right? So we're going to look at the 5. But 5 is too small. So 8 is bigger than 5, so we've got to search the right half of the array. So we're going to search from 3 to 4. And the midpoint of that is 3 plus 4 divided by 2 is going to be 3. So we look at the 7, but the number we're looking for is too big. So we look at the right half of the array, and we find there's only one item in that array, and that's when it's there or not. So 8 is 8, so the search ends. 8 is in the array. That looks kind of complicated, but I mean, if we just started, it only took us 1, 2, 3, 4 comparisons to find it. If we had just started doing a linear search, we would have had to look at 1, 2, 3, 4, 5 in this case. So it didn't really save us too much time, but compared to a linear search, if we were looking, say, for a 24, the binary search would get to that a lot faster with, on average, about like 4 hops or so. So it's actually really fast, and as you double the size of the array, you only add another hop to find the value or not, right? Because it's dividing it by 2 each time. You double the size of the array, you're just adding one more step to the process. So that's a log n big O. Question?
Does binary search require that the array is already sorted?
Yes, binary search requires the array to be already sorted. Yeah, if it's not sorted, then yeah, you can't make those judgments about which side of the array to look, which side of the midpoint to look. Right? You've got to actually have it sorted first. So the two go together. But binary search is a lot easier to comprehend than the sorting algorithms we're going to look at. Here's one that fails, and you can kind of trace this if you want. Again, we start looking at, you look at the 10, but 16 is bigger than 10, so now we can look at the right half. So the average of that is 17 over 2 is 8, so we're going to look at the 18. 18 is too big, so we're going to look at the left half of that. So 6 and 7, that gives us 12, but that's too small. So we look at the right half of the array, and then we end up with this one thing that says a 15 in it. 16 is bigger than 15, so we're going to search the right half of the array. That gives us like where the first is going to be bigger than the last. That means it's false. It's fine. So that's how it fails. So the efficiency of binary search is log to the base 2 of n. And of course, the best case is where the item you're looking for is right in the middle, so that's O of 1. But the worst case and the average case are O of log n. So think about how many compares to search for an item in an array of 1 million items. Anyone want to make a guess? How many searches it would have to make for binary search to find? How many items would it have to look at to find something in an array of 1 million items? Like 1,000 or so? 10,000? How many would it take? 60-ish? Well, remember what 2 to the 10 was? You remember what that is? 1024. 1 million is kind of like 2 to the 10 squared, right? So that's like 2 to the 20th. 20. It only takes about 20 compares on average to find any item in an array with 1 million items in it. The binary search will find it in 20 comparisons. 1 million items. That's actually really fast, right? That's how powerful a log n algorithm is. So the Java class library has a binary search algorithm in it in the arrays library, and that will the binary search in this one is going to give you the index of where the item is, and we're going to come back to this. It tells you a kind of a code on where it is if it's not in the array. Merge sort. We're going to look at merge sort today, or I think we can look at merge sort. We can look at merge sort later. Another one, because I'd like to get you to start coding now. It's almost 5. Maybe we should just dive in. Yeah, let's just get you coding now. We can look at towers of familiar tomorrow on Wednesday as well. I've been talking too long. Anyway, so what you got to do today is write some recursive methods, and you're going to go in the lab 8 file, and to begin with, you will write a method called valid input, and the idea for valid input is you're going to ask the user to enter a number between 1 and 10 inclusively, and your method is going to read that value in, it's going to print out the request for the data, read in the data, and then if it's acceptable, you return that value. Otherwise, you invoke it again recursively. You keep calling the valid input method with the value of 1 and 10, or 1 and n, until the user finally enters a correct value. Here's the display row of characters. You can try making a display array backwards algorithm recursively, and you can do it twice using those 2 different approaches. You can do a palindrome method. The coding bad exercises, put your solutions below and below main. You can copy them below main. And then the max value method, which I just talked about, you can solve that as well. So have at a go at it. The lab handout has some more hints, I think, on some of these things. Here's the algorithm for valid input. You're going to declare a scanner object set to keyboard inside that method. Ask the user input between low and high, inclusive, read the value, and either return the value or return a recursively invoked valid input to read a new value. Thanks, bud.